that add new functionality to existing distributed systems. And I'll come back to that later because that's what led into my work on aspects that I'll talk about later on also. The next big topic that I worked on was called interleaving sets. The idea is when you have a distributed program, very often there's one operation, one event that happens over here, another one that happens over here, and they're independent. And on the one hand. On the other hand, if you have two operations here, one after the other, those are ordered. So when you have an execution of such a system, there's a partial order among the different events that happen and among the different operations that occur. And various people have tried to exploit the fact that you have this partial order. And we noticed, or I noticed, that the way that people were trying to approach it was not necessarily the way that people really thought about programs, coming to, closer to what David Orell was talking about. That people actually think in terms of scenarios and express themselves in terms of scenarios, a particular sequence of events. Even if they come from different processes, they think of it as there was this one, then we did this one, then we did that one. In fact, it could be we could have done this one first and then that one. But they think of it in terms of a particular ordering of the operations. And if you think of all the completions of the partial order into a total order, there's a connection between those, that the only difference between those different linearizations, these different orderings of the operations, are that independent events that happen in different places are ordered differently. First you have this one here, and then that one, and the other one you do this one first, and then that one. And very often what you might want to do is to specify things and prove them by showing that you have these for each partial order, there's like an equivalence classes of all the total orders that fit with it, and each one can have a representative execution, and show that these representatives have some good property that you want, and then show every execution is equivalent to some representative. It's a different way of thinking about the collection of possible executions, and it's very natural for some applications, for example, serializability in databases. Serializability in distributed databases just says there is a particular ordering where you do all of this operation, then even though they're in different parts of the system, and then all of what corresponds to the next complex operation, even though they're in different parts of the system. And you can do them one after the other, even though in practice they really might be an execution where you mix them together, these different operations, the different parts of them. And you can, that doesn't matter, because all you're doing is changing the order in which you did independent operations. And that's what people in database do when they show that some distributed implementation of is serializable. So we worked on this for years and developed proof systems and model checking techniques. This was Doran Pellet worked with me on this kind of subject, also Marcelo Glusman. We both did PhDs on that. Doran went on to continue the ideas of partial order in model checking in different contexts, and today he's working on even different subjects. But that was a nice activity, and again, in this general framework of trying to take something kind of natural and try and understand it, prove things about it, and break it up into simpler things. And here again, this is just an illustration. Here that you have a state of the system, an action, and here you come to this state. Here you do this action, and then you do these, and here then you switch, and you switch, and you switch, and you can get to this other one where you do tau 2, 3, and 4, and then 1, and you get to the same state over here, and those are equivalent. Anyway, it was an interesting line of research. Okay, another completely different direction that we worked on was Veritech. This was a multi-year project that I worked on with Orna. And the idea is there are a lot of different tools that are used to analyze software. Okay, and the formal methods tools. And each one is good for different things. And very often you want to prove one property using one system, and then use another tool to prove another, a different property. It's just not handled by the first one. And you have to translate from one to the other, the model. And the problem is that when you do this translation, sometimes something that you showed was an invariant in one version, after you translate it, it's no longer an invariant, because there you had really big, thick atomic operations, so something is true in every state, and to do the translation, you have to do several operations, and then in those intermediate states, whatever you wanted to show is no longer true in those intermediate states. So you have to translate the properties along with the representation. So here, these, for example, are all kinds of tools from around the world that we imported, and people originally had to try and translate from one to the other directly. And our idea was to break this by having a core that each one would translate into and translate back. And then you have a new system, you just come and plug it in, and you could get, very nice idea. It didn't always work, but usually did. The base idea was instead of having n squared translations, you have n. I've exaggerated the size of n squared relative to n, but anyway, that's the idea. You have a lot fewer translations. And again, the idea was to simplify, to allow you to do a variety of things using different tools, and to sort of conquer the complexity that's going on here. Okay, now finally we get back to superimpositions. These are additions over a distributed program that give you new functionality. And there are all kinds of well-known examples: distributed termination, self-stabilization, where you have an algorithm that is, for example, the self-stabilization, you have an algorithm that does something, a distributed algorithm sending messages back and forth, and all of a sudden, and you want it to be self-stabilizing. It means if all of a sudden you change the memory, or you change the values of the variables in an arbitrary way, so that it no longer reflects what the program has been doing, and then just continue executing, will it get back to a normal state and be able to continue? And if the program is self-stabilizing, it will be. And what we tried to do was write an addition to a regular algorithm that will take a regular algorithm and make it into a self-stabilizing version. We showed that you can do that if the program has a very special form, and if it's in a restricted way, you can do it. And again, that's kind of an addition. You add different things in different parts of the program in order to get a new functionality. Okay, and that brings us to aspects, which is what I've been working on for the last 15 years, more or less. The idea is that aspects are really like the superimpositions, but for object-oriented systems. We first pointed this out, this connection, because the two communities were completely unaware of each other. We pointed this out in a short paper with Yossi Gil. It's like a 3-page note. It became one of my quoted papers because everybody said, oh, gee, there really is a connection between these two things. And again, aspects are a new kind of modularity that cuts across additional modules. And the idea is you have some new functionality you want to add on. And you need to do a little bit here, and a little bit here, and a little bit over there in order to get it. And instead of going in and changing everything, you describe on the side, whenever such and such happens, I need to instead do something else, or I need to add this other thing in addition. Whenever this other thing happens, I need to do something else. So that's the idea of it. And you declare that once and for all, and then you have a regular system. You say, all right, I want to apply this aspect. So then you sort of weave it into the existing system using a sort of compiler. And you can use it for all sorts of good things. We tried to show the problem was that people looked at these things as system hacks, just hacks, and we showed that it's actually a program transformer. You get in the program without the aspect, you apply the aspect, and you get out a program that has this additional functionality. So why did I find aspects interesting? First of all, they're a challenge because they add or change existing code in many locations, but they're declared separately. They sort of don't do anything on their own. They have to be added into something else. But can you show that they're correct on their own? They're seen as useful, but many people don't use them because they're afraid of the reliability and unexpected effects they might have. And actually, I saw that this